Hey everybody, in this video we are continuing to discuss AP Calculus Unit 6 on integration and accumulation of change. So let's pick up where we left off from the last video and let's talk about integrals. We have definite and indefinite integrals. So what are they? Well, we have two integrals here and they have one difference, right? This guy has from A to B and this guy doesn't. This is what we saw at the end of last video, right? This is what we call as this is what we call a definite integral, because it has these it has these definite boundaries, right? This guy up here is called an indefinite integral, and it's sometimes known as an antiderivative. So antiderivative should tell you it's like, okay, well, it's the opposite of a derivative. And that's exactly what integrals are. They're opposites of derivatives. Now that's not obvious. That is not at all obvious. I can probably make a video kind of on that. It's really hard to kind of show, but I could probably figure out some video. But this is an indefinite integral. This is a definite one. This is easier to understand because it's basically just the area between a and b of f of x. That's pretty much it, right? So that's that. This guy, it's like the area between what? It's just the area of f of x, but we don't really know from where to where. Well, that's kind of, you know, this actually is harder. It requires more steps, and I'll show you kind of some examples. But really, this indefinite integral is going to give us, like, if we take the integral of a function, it's going to give us, like, another function, right? And what we do with that other function is we plug in these boundaries. So essentially, if we're given, so actually, with the knowledge that it's an antiderivative, let's say, so we know the derivative of x squared is equal to 2x, right? We already know this from like unit 2, right? So, but the integral of 2x is x squared. So that's pretty easy, right? But then we're going to add a plus c. So this c is a constant. And you're like, where does that come from? Well, it's actually not too hard to describe, because the derivative of a constant, right? So maybe actually, yeah, if we had like the derivative of, let's say, x squared plus 5. So this is our original function. We're going to take the derivative, and we actually still get 2x. So the derivative of a constant just goes away. We lose that information. So this integral, we actually can't like recover that information. So we say, well, we're going to add a c, some number c that we don't know what it could be. It could be any real number. We haven't made that determination yet. There are ways that you can make that determination. I'm not going to describe that in this video. I might describe that for unit 8 or 7 even, I think. But yeah, so there are ways, but for now, we just know that it's x squared plus c. And maybe the c is equal to 0, so then that's when we're left with x squared. But we don't know about that. And so you can kind of even look at, like, you know, if we have a function here, right, the derivative doesn't care about your position. It does not care. Like, if we draw the exact same curve, let me really try to draw the exact same curve here. Something like that, right? If we have, yeah, it's not really that great, but it's close enough. If we have the same point here, it's going to have the same slope. Actually, I should have drawn that like over here, but whatever. It's going to have the same slope, but it doesn't care about the position. So that's why it kind of just goes away. But here, the area will care about the position. The area between this guy and this guy is a lot less than the area between this guy and this guy, like this whole guy. So, you know, that's kind of what we do. So yeah, we just get a function as our output, right? So let's see, what do I want to do? So pretty much, if we want to find the area of under x squared from 1 to 2, so let's say we want to find, of 2x, so let's say we want to find from 1 to 2 the area under 2x, right? So this is going to give us x squared, but we're going to evaluate this guy, I like to do it like that, from 1 to 2, right? And so we're evaluating this from 1 to 2, and I like to kind of put this, this like bracket on this side because that kind of closes it off, or it starts it off, and this guy closes it. So we're going from 1 to 2, and you might be like, where did the plus c go? Well, I'll show you why, where it goes. So actually, yeah, let's do that. Let me add that plus c. From 1 to 2, right? So what we do is we plug in this first bound, and then subtract off, we'll plug in that bound. So this is going to be equal to, so we have 2 squared plus c. Again, we don't know what c is, but then we're going to subtract off 1 squared plus c, right? So basically we're going to get 2 squared is 4, so we get 4 plus c minus 1, and then minus c. So as you can see, the c's cancel out, and we just get 4 minus 1, which is just 3. So the area under 2x from 1 to 2 is 3, and these are your x values, of course. And so that's pretty easy. So that's how to find an integral. Now they get a lot more complicated than that, but that's kind of what I wanted to show you. So essentially, if we have the area from a to b of f of x dx, this is going to be some other function. We'll call it capital F of x, right? But then we're going to evaluate it between a and b. So exactly like what I did earlier, from a to b, and that gives us, so f of b minus f of a, or capital F of b minus capital F of a. So this is what's known as like part 1 of the fundamental theorem of calculus. So I'll just write it as FTC because that's what it's often abbreviated as, fundamental theorem of calculus. This guy is really important. Now the other part is kind of, actually, I don't know if I want to cover it in this video. We'll see. But yeah, so I kind of just wanted to show you that part. Now let's talk a little bit more about integrals, right? Because we saw that the integral of 2x is x squared, but what if we have like some other polynomial, right? So we do have some more types of, you know, rules and stuff. We actually don't have a lot of rules for integrals, so it makes them a little more difficult. Like there isn't a product or a quotient or a chain rule. There kind of is a chain rule, but not really a product or a quotient rule, so it makes it a little more challenging, but it's a little more creative, you know, trial and error sometimes. But yeah, so the integral of x to the n dx, right? So n is just some number. It could be a real number. It could be an integer or a real number. It doesn't matter. So x to the n. So remember, with the derivative, it was nx to the n minus 1. So here we're going to be doing those two rules in reverse, but then we're going to do it in opposite order. So remember, for derivative, actually let me write down the derivative. So the derivative of x to the n is equal to, first we hop this guy to the front, so n times x to the n minus 1. So we hop this guy to the front and subtract by 1. Here we're going to add 1 and then divide by that same number. So, and then plus c, of course. So pretty much, again, we're doing it in the opposite steps in the opposite order. So here we first multiply and then subtract. Here we add and then divide. So yeah, it's pretty weird. It takes some getting used to. Make sure not to like confuse the two, because it's pretty easy to confuse them. But after you do a lot of practice, you'll be fine. So that tells you, so you know that the derivative of sine is cosine, right? So sine, I'll use theta, why not? d theta of sine of theta is equal to cosine of theta. So the integral of cosine of theta, d theta, and the d also serves as a good way of saying, like, what are you integrating with respect to, right? So this is going to be equal to sine of theta plus c. Again, c is just some number. So these are some important things. And again, we don't really have a quotient rule or anything, so it does get a little more complicated. But yeah, or even a product rule. So let's just let's move on to the next section, and I'll show you some integration techniques. So some integration techniques. First is know your derivatives. Okay, I kind of stole that from black pen, red pen, but just know what the derivatives are. So derivative. So you know that the sine, its derivative is cosine. So the integral of cosine is sine. The integral of these guys is these guys. It's pretty simple. Now I have 1 over x here. The derivative, the integral of 1 over x is going to be ln of the absolute value of x. So let me say ln of absolute value of x. Now the reason why that's a distinction is because when we had the ln x, whenever we were taking the derivative of it, we kind of assumed that its input would be positive since that's its domain restriction. But here, we have to make sure when we're integrating 1 over x that you put the absolute value bars inside. So let's see, and of course you would add plus c to all of these. So that's pretty much it. So know some of your derivatives, and again, that formula from earlier about the polynomials, that's also important. Let's see, what else do I want to add? Well, not really anything else. There's no product rule, there's no quotient rule, but there is kind of a similar thing to the chain rule, and it's called U-substitution, or integration by substitution. That's the more formal term. But U-substitution is used because you substitute a U. So let me just kind of talk about this. So whenever we were taking the derivative of the f of g of x, you get f prime of g of x times g prime of x, right? So let me write that down. So now what we do is, if we have the integral dx, this is going to give us back f of g of x. Well, what are we missing? What are we missing? Plus c. And there we go, right? So this integral is going to give us that. Now this is really hard, so we like to simplify it. We like to say, okay, well, if we say u is equal to g of x, then we can say, okay, well, then we're going to have integral of f prime of u, right? But then we need a du, right? Because we're no longer dealing with x's, we're dealing with u's. So we need to find what our du would be. So how would we find what a du is? So let's just take the derivative of this guy on both sides. So we have u prime of x, which is equal to du over dx, right, is equal to g prime of x, right? G prime of x. Okay, so I'm going to ignore this u prime of x because it's easier to deal with this du over dx, right? And so we're going to multiply both sides by dx, so we get du equals g prime of x dx. Let me just copy that back up here. So du, and you're like, well, can you really separate it like that? Well, yeah, technically you can treat this guy as a fraction. It's not totally proper, but I mean it's an actual method of doing this. So yeah, it works. So it's called separation of variables because you're kind of separating it. But yeah, it works. So we have du equals g prime of x dx. That's exactly what this is, right? So we have f prime of u times du, right? Because we made that substitution. And this kind of lends us to another idea, that the integral of a derivative is basically the original function. So we get f of u back. And f of u, we said u is equal to g of x, this is, and of course plus c, never forget plus c. This is equal to f of g of x plus c. So that's kind of the whole thing of U-substitution. I'll show you an example in a second, but first I do want to say, yes, the integral of a derivative is the actual function itself. So interesting idea, right? And of course the derivative of an integral is also that. And it gets a little weird with indefinite integrals, so I'm going to show you that in a second. But let me give you an example of U-substitution. So we have an example. If our integral is, 2x times e to the x squared dx, right? We can say, okay, well, let me put the u over here. We have to choose our u kind of based on what we think, like, okay, well, we need a g of x and a g prime of x. So let's say if our g prime of x, maybe it can be like this x squared, right? So let's try that. U is equal to x squared, and our du is equal to 2x, right? Derivative of x squared is 2x, and of course we need that dx, right? So that's exactly what we have, 2x times the dx. And so then this reduces to e to the u, right? E to the u times du. That's kind of the whole premise of this. Now, like this may be a little weird because it's like, whoa, what are we doing here? But I just want you to kind of understand what's going on. And it's typically good to choose a u that's like in the exponent or denominator or inside of another function. And I'll show you an example in a second. So we know e to the u, the integral of e to the u, is e to the u plus c. But of course, we need to go back to the x's because we just made up a u. So this is going to be e to the x squared plus c. And that's our answer. And so if we take the derivative of this guy, we get that back. The 2x e to the x squared. Another example, yeah, I'll just do it down here. Another example is the integral of, let's say, x plus 1 to the 20 dx. And you're like, whoa, that's a lot. But if we do u equals x plus 1, then our du is actually just dx, right? Because the derivative of x is 1 and the derivative of 1 is 0. So we just get du equals dx. So that's pretty cool. So what we have is just the integral of u to the 20 du. Because like x plus 1, we can't work with that. Like it's a function inside of another function. So now we just can use our power rule, the polynomial rule. And so again, remember, we add one first. So it's going to be u to the 21st over that 21. And let's change it back. So this is x plus 1 to the 21 over 21 plus c. And so yeah, sometimes your answers can get crazy, but it really just kind of depends, and definitely do a lot more examples. Paul's online math notes has a bunch of examples. Wolfram Math Generator, Problem Generator, I think, has a lot of examples, so just do a lot of examples. But yeah, I think we have time for one more section, so let me talk about that. Okay, so this is what we already established, right? Now, another part of the fundamental theorem of calculus is saying, like, okay, well, if we take the derivative of an integral, and this goes from a, actually not a to b, let's say it goes from, u of x to v of x, which these are both functions of x, of f of t dt, right? So we're using different variables. It wouldn't make sense if these guys were also x's, so just keep that in mind. But the derivative of an integral, of an indefinite integral, the derivative of an integral of a definite integral, I'm sorry, this is a definite integral. The derivative of an indefinite integral without the bounds is just gonna straight up give you the function back. But the derivative of this guy with these bounds will not give you that back. It'll be similar, but not quite. So remember, based on this is going to be, again, the derivative, but of, we'll have capital F of v of x minus capital F of u of x, right? And so the derivative of this is going to be capital F prime of v of x minus capital F prime of u of x, right? So we just do that, we apply kind of some rules. We know that capital F prime is just, since it's the derivative of our integral, so this is just going to give us back f, lowercase f, of v of x times the derivative of the inside, right? So v prime of x, make that v a little better, minus f of u of x times u prime of x. And you're like, this is a mess. But what I like to reduce it to is f of v dv minus f of u du. This is a nice little way to reduce it, just so it's not crazy like that. But yeah, this is kind of just that's the derivative of an integral, right? But the integral of a derivative, so if we have the integral of a derivative, so d over dx of f of x dx, this pretty much, so from a to b, so you're taking, okay, so this is going to be a to b of f prime of x dx, right? That's what d over dx of f of x is, f prime of x. And so we know that this is going to be, well, this guy's derivative, so if this is the derivative, the integral of it is just going to be the original f of x itself. So f of x evaluated from b to a, so it's going to be f of b minus f of a. And so these are some parts of this. And actually, one thing I want to mention for this is if this guy is just a constant, if u of x is a constant, this part, the derivative of a constant is 0. So this part actually just goes away. And what's more, if this v of x is just equal to x, this guy, or this guy, whichever you want to look at it, it's going to be f of x times, well, the derivative of x is 1, right? So it's just going to be f of x. So if you're taking, let me actually put like a corollary. So the integral, the derivative of the integral from a to x of f of t dt is equal to f of x. Not plus c, because we have these bounds, it's just precisely equal to f of x. So that's a nice thing. You'll see this more often than this, but this is more complete, and there are some problems that you need to know these formulas. So I don't want you to memorize them, the formulas, just kind of understand them. That's how you get them. So yeah, sorry these videos were long, but we'll see. I hope it really helps you. So thanks for watching, and I'll see you in the next video. Bye guys.